Hello and welcome to another geometry read-along. Today we go through section 3.4 on surface area. So our applied problem to start us off involves a hopper designed to store wood chips and empty them into trucks. Has the shape as shown. How many square feet of metal were used in its construction, including material for the top? So imagine this was constructed out of folding up a large sheet of metal. How much total gets used? In sections 3.1 and 3.2, we discussed areas of regions in the plane. Now we will extend that idea to shapes in 3 dimensions, although they are all still composed of 2-dimensional shapes. More on that later. So the surface area of a right prism is our most basic of shapes, so we'll start there. The surface area of a polyhedron is the sum of the areas of its lateral faces and bases. SA is an abbreviation for surface area. So that is not only an excellent definition, but it summarizes the whole idea used throughout this entire section. In fact, the rest of this section is mostly going to be derivations of shortcut formulas. Okay? You can always still go back and apply this idea of add up the areas of all the faces. So, for example, the surface area of this right rectangular prism shown here, we've got length 8, width of 5, and height of 4 centimeters respectively. So the area of each base is 8 times 5, or 40 centimeters squared. 2 of the lateral faces each have an area of 4 times 5, or 20 centimeters squared. And 2 have an area of 8 times 4 equals 32 centimeters squared. So the surface area is 2 times 40 plus 2 times 20 plus 2 times 32 equals twice the sum of 40, 20, and 32 for a total of 184 centimeters squared. Notice that we could express the surface area of the right rectangular prism from the example as follows. Surface area equals twice 8 times 5 plus 4 times 5 plus 4 times 8. We have factored out that 2 since we know we have a duplicate of each face. And if we separate out the base from the lateral sides, what we end up with is 2 times area of the base plus the perimeter of the base times the height. So look what they did there. 2 times the quantity, 4 times 5 plus 4 times 8. We distribute that 2, and then we factored out the 4 instead, since we had the matching 4 there. Because the 4 was the height of the figure, and now 5 plus 5 and 8 plus 8 makes the perimeter around the top. So we get 2 times the area of the base for both bases, plus perimeter times height. Okay. This result holds for any right prism. That is, the base need not be a rectangle. See? So that generalization allows us to look at this. The surface area of any right prism. And remember, a right prism is one whose lateral faces are perpendicular to the base. It's not a slanty guy. So the surface area of a right prism is the sum of twice the area of its base plus the product of the perimeter of the base and the height of the prism. Okay? So if you can remember that or have it an easy reference in your notes, twice A being the area of the base, plus P times H, P the perimeter, and the total height. That can save you a little bit of calculating there. Now, how about pyramids? The surface area of a pyramid is the sum of the areas of its base and lateral faces. Okay, that sounds like another good solid definition to me. A pyramid is still a type of polyhedron. So, for example, find the surface area of a right regular triangular pyramid if the sides of the base are 6 centimeters and the slant height is 8 centimeters. Okay, so right meaning The height here is centered above the center of its base, and the base itself is a regular triangle, so an equilateral. So we know the sides all the way around are 6, and the slant height, so the height of a side face, so here we have the base split apart and the side lateral faces of the pyramid. Okay. Pyramid is a right regular triangular pyramid, therefore its base is an equilateral triangle. Using the Pythagorean theorem, we have h squared plus 3 squared equals 6 squared. So we're trying to find this perpendicular distance across, so we split this into two half right triangles. Or h squared equals 36 minus 9 equals 27. Thus, h equals square root of 27, or 3 root 3. And the area of the base is 1/2 base times height. So 1/2 times 6 times 3 root 3, total of 9 root 3 centimeters squared. Notice we could also find the height of the base by observing that the base is divided into two 30, 60, 90 right triangles. Use your special triangle shortcuts there. The three lateral faces are identical isosceles triangles, shown here in C. The area of one face is 1/2 6 times 8 for 24 square centimeters. Thus, the area of all three lateral faces is 3 times 24, or 72 centimeters squared. The surface area, the sum of the areas of all faces, is 9 root 3 plus 72, or approximately 87.6 centimeters square if we go out to one decimal place. So let's generalize again. We can express the surface area of the pyramid as follows. We had the 9 times root 3, that was the base, plus 3 times the area of the faces. And what they're doing here is we distribute that 3, well, really it's just all multiplication. Okay, so it's really an associative property here to set apart. We arrange, so this is the area of the base, 9 times root 3, and then put the half in front and pull the 8 out to the side. 1/2 stays there. This 3 times 6 is now the perimeter of the base. Okay. We get 3 of these sides here, and 8 is that slant height. So 1/2 times perimeter of the base times the slant height gives you the lateral face summation. So now this result holds for any right regular pyramid, regardless of the shape of the base. We find the surface area of a pyramid with a base that is not regular by adding the areas of the base and the lateral faces. Okay, so only if it's a regular one will this work out, because for a regular pyramid, the lateral faces are all identical. If it's not regular, you don't have identical faces, and you can't use this multiplication trick. You will have to add them the old-fashioned way, but that's okay. So go ahead and add this shortcut formula to your notes as well. Surface area, oops, there we go. Surface area of a right regular pyramid, okay? Both of those must be true in order for this to work. Area of the base plus 1/2 perimeter times L, the slant height. All right, next we move into the realm of round shapes. We can find the surface area of a cylinder by adapting the formula for the surface area of a prism as suggested by figure 3.33. Imagine increasing the number of sides of the bases of the prism so they approach a circle. All right, you can see there as we progress from 4 sides to however many, 12 sides, up to almost infinite sides. Okay. In this case, a right circular cylinder whose base has radius r. A represents the area of that base, which is pi r squared, and P represents the perimeter, which now is C, the circumference of a circle, which we know is 2 pi r, so still based on r. And this leads to the following theorem. The surface area of a right circular cylinder, taken from this equation and adapted for circle-specific names for things, can be simplified and reduced down to twice the area of the base plus circumference times height, or 2 pi r squared plus 2 pi r h. Go ahead and add that one to your notes. So, for example, let's find the surface area of a right circular cylinder whose height is 7 centimeters and whose base has a diameter of 12 centimeters. This might be well, it's kind of it's a little bit short, fat kind of a can. Maybe some kind of coffee can. I think I got some powdered hot cocoa in something about this size. So the surface area would be 2 pi times 6 squared plus 2 pi times 6 times 7. Right, remember the radius is half the diameter, and there's our height there in 7. So 72 pi plus 84 pi gives us a precise answer of 156 pi centimeters squared. You can, of course, use the approximation for pi if you want to get a decimal approximation. How about a cone? As in the case of the cylinder, we may find the surface area of a cone by adapting the formula for the surface area of a pyramid, as suggested in figure 334. So here we go from 4 sides out to 10 or 12, and out to infinite sides. So we get an infinitely skinny triangle up here to form the cone face itself. So, in the case of a right circular cone, where r is the radius of the base, a represents the area of the base, namely pi r squared, and c represents the circumference of the base, 2 pi r. Also, L represents the slant height. By substituting for A and P in the formula, A plus 1/2 PL, we can arrive at a formula for surface area of a right circular cone. Again, you can still use this just as well. Just recognize, how do you find the area of a circle? And how do you get what is another name for the perimeter of a circle in particular? We get this. Surface area of a cone, A plus 1/2 CL, or pi r times r plus L. So note there in the derivation they've filled in pi r squared and 2 pi RL, and you could factor out the pi from both, or pi and r from both terms. And 1/2 times 2 reduces. We get a very lovely simplification there. Go ahead and add that one to your notes. Surface area of a right circular cone. Yes, it must be perfectly up and down. So, for example, find the surface area of a right circular cone whose height is 8 centimeters and whose base has a radius of 6 centimeters. We've got a nice picture here on the side of what that would look like. First, find the slant height L. Oh, yeah, they didn't give us that. They give us the actual height, which is great for finding the volume. More on that later in a totally different video. But we need this slant height for the actual surface area. But notice from the side view here, this is clearly a right triangle shown, and so we can use Pythagorean theorem. L squared will be equal to 6 squared plus 8 squared, or 36 plus 64 equals 100, which means L is 10. We could also observe that 6 is 2 times 3, 8 is 2 times 4, hey, 3 and 4. Thus, L must be 2 times 5, or 10, because it's the hypotenuse of a right triangle whose sides are multiples of the 3, 4, 5 special right triangle, a Pythagorean triple, and multiples thereof. That would save you a little bit of calculating here. So now the surface area is pi times 6 squared plus 1/2 times 2 pi times 6 times 10, for a total of 36 pi and 60 pi, 96 pi centimeters square overall. Or you can use the shortcut result, pi r times r plus L. We could also do it that way, pi times 6 times the quantity 6 plus 10, or pi times 6 times 16, which is 96 pi centimeters squared. That checks out. All right, and last but certainly not least, we have the surface area of a sphere, the roundest of round objects. The derivation of the formula for the surface area of a sphere it's rather complex, actually. In fact, a true derivation will involve a little bit of calculus. However, the following observation, due to Archimedes, simplifies the task of remembering the formula. Good old Greek mathematician Archimedes. Consider the smallest right circular cylinder containing a sphere of radius r. Because the sphere has radius r, the base of the cylinder has radius r, and the height of the cylinder is 2r. Therefore, the surface area of the cylinder will be as follows. So yes, if you make a pan as teeny tiny as possible, whose edges just barely touch and just barely fit this ball inside, these are the dimensions you will get. And so the cylinder's surface area would be, using our cylinder formula, 2 area of the base plus circumference times height, 2 pi r squared, plus 2 pi r times 2r, for a total of 6 pi r squared. Archimedes' observation was that both the surface area and the volume of a sphere are 2/3 the respective surface area and volume of the smallest right circular cylinder containing the sphere. Right? He did this a little bit more empirically, dealing with weights and balances and volume with displaced water and such. But it still holds. We could use, this is where the complex derivation comes in, proving that principle. Okay? Surface area and volume of a sphere is 2/3 that of the similar sized cylinder. Thus, the surface area of the sphere of radius r can be found with the previous equation, 2/3 times that cylinder, so it's 2/3 times the 6 pi r squared from up here, for a total of 4 pi r squared. Okay? I like to think of it as, since a sphere is basically a circle in 3 dimensions, we take one of our circles and we slap it in one for each direction and add an extra one to fill in the gaps. And you can wrap your sphere out of 4 circles of the same radius. So surface area of a sphere now is 4 pi r squared. Go ahead and add that formula to your notes. And that one, with the rectangular prism and pyramid, are probably the most commonly used cones and cylinders to follow. And then the other regular regular right prisms and pyramids. So how about an example with the sphere to wrap things up? Although estimates vary, water covers about 70% of the Earth's surface. About how many square miles of the Earth's surface are composed of land? Okay. So from section 2.5, we found that the radius of the Earth is approximately 3,964 miles. Thus, the total surface area of the Earth is 4 pi r squared. So about 4 pi times 3,964 squared, or to the nearest mile, or nearest square mile, 197,459,101. 70% of that is water, then the land covers 30%, so take 0.3 times that result to get approximately 59,240,000 square miles. That sounds like a lot. But remember, not all that's usable. You got mountains and deserts and such in there. All right. So back to the hopper from the beginning. We need to find the surface area of this right hexagonal prism. Oh, it looks like some funky kind of shape, but notice all of these sides, right, connect 2 parallel faces there. So yes, it is a right prism, and in this case specifically hexagonal. So using the Pythagorean theorem to solve for x in the figure, solving for x, what are we missing there? Because we need to get the area of the base. So we're going to divide that into a large rectangle, a smaller square, and 2 little triangles. And no, we don't need this diagonal to find the area of this triangle, but we will need it as the edge of this rectangular lateral face. So we'll need that for the whole perimeter. Simple enough. We divide this up taking this 8 across and transferring this 3 up there, keeping everything square and parallel. All right, 3 more to make this a right triangle. These pieces become 2.5. So 3 squared plus 2.5 squared to give us x squared, or x is about 3.91 feet. Thus, the area of these 6 rectangular faces is given by area equals perimeter times h, or area is going to be 8 plus 10 plus 3.9, so we're just going around, adding them up, plus 3, plus another 3.1, plus another 10, all times height of 18, for a total of 698.76 square feet. The area of the 2 bases, then, is 2 bases, each of which has an 8 by 10 plus 1/2, 3 times 3 plus 8, treating this whole lower section as one trapezoid, using the formula there, for a total of 193 square feet. Thus, the surface area is approximately 193 plus 698.76, 891.76 square feet. And one last thing before you go, a little bit of geometry all around us. Some porous materials with large internal surface areas are important in many applications, including gas storage and the production of fuel cells. In 2004, U.S. researchers created shaped crystals. See the figure over here. That's interesting. Reminds me of the flux capacitor. That have surface areas of up to 4,500 meters square per gram. Remember, a gram is about the weight of a paperclip. By comparison, a human lung has surface area of about 0.25 square meters per gram. And think of how much air we can breathe in at once. The surface area of a whole tennis court is 196 meters square. This thing has order of magnitude more surface area in a single gram than a whole tennis court. One obstacle faced by the automobile industry in the transition from fossil fuels to hydrogen is finding an efficient way to store the gas. The fact that the new crystals can bind large volumes of gas in a small space offers a possible solution to the hydrogen storage problem. Although by now, electric cars are really taking off. For a while, people thought maybe we'll go to hydrogen. It is a fantastically efficient fuel if only you can find a box to keep enough of it in. This may be the solution. Geometry is in our future. So thanks for reading along with me. So long, farewell, enjoy the rest of your day.